Okay, so looking at some thermal physics, in order to observe Brownian motion, or Brownian motion being the random movement of particles in a liquid or a gas, some smoke is mixed with air trapped in a small glass box. The box is strongly illuminated from the side, and the smoke is viewed above through a microscope. We've got a diagram to show us that. Describe what is seen when the microscope is focused on the smoke particles. So what you see is the smoke particles moving randomly and rapidly, or moving very quickly. So the key thing here is you cannot see the air particles, but what we can see is the effect of the air particles on the smoke, because the smoke is much bigger, so we can actually see it with a microscope. So air is moving randomly, which is why we see the smoke particles moving randomly too, and we see the smoke particles constantly changing direction every time an air molecule is colliding with them, which is very often. State what causes the effect described. So this is basically what I was just saying, but let's put it into words. So smoke particles change direction when they collide with a high-speed air molecule. And the air molecules are moving randomly around the smoke particles. Okay. So the temperature of the glass box and its contents is increased. Suggest what change is seen through the microscope. So higher temperature means the air molecules will move faster, so the smoke particles will therefore move faster, which would mean they change direction more frequently, because there are more collisions per second, if you like, with the smoke particles. Okay, so the diagram shows a mercury in-glass thermometer calibrated in degrees Celsius. What temperature would the thermometer read if it's put in steam just above boiling water at standard pressure? Well, the temperature at which water turns into steam is 100 degrees. What temperature would the thermometer read if it's put in pure melting ice? Well, 0 degrees. Mark on the diagram where the end of the mercury thread might be when the thermometer is in a freezer, where the temperature is well below the freezing point of water. So we could pick anywhere below 0 degrees, so I'm going to pick this one here. As long as it's clearly below 0, that's fine. Mercury in-glass thermometer uses the expansion of a liquid to measure temperature. State another physical property that can be used to measure temperature. So the other one that we come across as part of the course is the potential difference across a thermocouple. So I think that's what they're looking for in answer. We could use all sorts of things to illustrate it. We could use like the pressure of a gas. That would work. We could use the size of a solid in a bimetallic strip. There's loads of different things, but I think this is one they're probably looking for. So air trapped in a cylinder by a piston is kept under pressure by a load, as shown in the diagram. Okay. Describe how the pressure in the cylinder is caused by the air molecules. So the key is that the pressure is caused by the collisions between air molecules and the container wall. That's the source of pressure. And all of the collisions are spread over the whole surface area, which is why we talk about them as a pressure rather than as a force. So each collision exerts a force, but because there's collisions spread all over an area, we talk about a pressure rather than a force. The load is increased to state what happens to the piston. So it's going to move down and decrease the volume of the gas inside the piston. State what happens to the pressure in the cylinder and give a reason. So the pressure is going to increase, and the reason is if we decrease the volume of the container by compressing it, there'll be more collisions per second because the distance each particle travels between collisions is now smaller, and the total area over which the collisions are spread is also now smaller because we've made the container smaller, and that's going to give you higher pressure. So the apparatus shown in the diagram is set up in a laboratory during a morning science lesson. So we've got a flask with air trapped in it, and then that is pushed down into water. So we've essentially trapped a fixed volume of air. Okay. So later in the day, the room temperature is higher. What change is observed in the apparatus? Well, the water level inside the tube is going to go down, because what's going to happen is the air it's trapped is going to expand because its temperature has increased, which increases pressure, and that would force the liquid down in the tube. So that's why. So the air pressure above the water increases and it pushes the water level down, and that's why we see that effect. So just one disadvantage of using this apparatus to measure temperature, well, it's going to take quite a long time to adjust. It takes time for energy to be transferred to the air to expand and to push the liquid. So it's quite a slow response time. And the other thing is, when you reach a certain temperature, the air is actually going to be pushed out of the tube entirely, and the bubbles will start escaping, and your equipment is no good anymore.
Okay. So we've got a thermocouple that's going to be used to measure the temperature of the inner wall of a pottery kiln. In the space below, draw a label diagram of a thermocouple that could be used for this purpose. So there are essentially a few key features of a thermocouple. You have the point where the two materials are joined together, which is what we call the hot junction, and that's where you'll actually measure the temperature of something. So you would put that on the wall of the pottery kiln. So you have two materials, and usually we use copper and iron. Now we have them going to somewhere that's at the same temperature, which is often referred to as the cold junction. So these two would be at the same reference temperature. It might be dipped in ice or something that's at fixed temperature. And then what we have is those two ends are connected to a voltmeter, or usually a millivoltmeter, as a way of detecting the potential difference between those two ends. Okay, so describe how you would read the temperature of the wall from the thermocouple. So the first thing you would do is you'd measure the potential difference using a voltmeter. So the question is, how do we then turn that potential difference into a temperature? Well, what you do is you would go to your calibration curve. So some of you may have done an experiment where you calibrate potential difference and temperature and plot a graph, and you basically go to that, you take the potential difference and you read off the temperature from your calibration curve. So describe how a thermocouple works. Well, a change in temperature causes a potential difference between the ends of the wires. Fundamentally, this is down to electrons diffusing by different amounts in the different materials, but the key is it produces a potential difference, and that's what you can measure using a voltmeter. State two conditions in which a thermocouple is very suitable for temperature measurement. So thermocouples are very good for measuring high temperatures, higher than a liquid thermometer would be able to, because they are limited by the boiling point of whatever liquid you use. And they're also good for measuring rapidly changing temperatures. The thermocouple response time is very, very quick, so it can measure temperature changes very easily. So in an experiment to find the specific latent heat of water, the following readings were taken: the mass of the water before the boiling starts, the mass of the water after boiling finishes. We've got the voltage across the heater, the current through the heater, and the time that the energy was supplied. Using the symbols above, write down an equation that was used to find the specific latent heat of water. So the equation we can start off with is Q equals mL, because we're dealing with a state change. So we can rearrange that to make L equals Q over M. So to find the energy we've supplied, we first need to figure out the power of our heater, which is current times voltage. To turn that into energy, we then multiply that by the time. So IVT calculates the energy we've supplied. We also need to work out the mass that has actually changed state. So that would be the difference between the two masses, M1 minus M2. Use the equation to calculate the specific latent heat of water from the readings. So we can basically plug our numbers into the equation, and then we get this value, which is going to be in joules per gram, because all the masses were in grams. We could have calculated it in joules per kilogram. If we'd converted, that would be fine too. As long as you give the unit correctly, that's fine. Explain in terms of the energy of the molecules why specific latent heat of water has a high value. So there are strong intermolecular forces in water. So every molecule is bound to every other molecule by a very strong force. And so if you're going to allow those molecules to escape, you have to give them a large amount of energy, so their potential energy increases enough that they actually can escape. So this is fundamentally why you have to supply a large amount of water, energy even. So equal volumes of nitrogen, water and copper at 20 degrees are heated to 50 degrees. Which of the three will have a much greater expansion? Well, it's going to be the nitrogen, because it's a gas. Explain your answer in terms of the way the molecules are arranged. So copper is going to be a solid at that temperature, so there are very strong forces So the expansion is going to be minimal. Whereas water, it's a liquid, so there are still strong intermolecular forces, so your expansion is going to be small as well. Nitrogen is a gas where there are very weak, if any, intermolecular forces, so expansion is going to be very great. So the diagram shows a thermometer with a range of -10 to 50 degrees. Explain what is meant by the sensitivity of a thermometer. Well, it's the change in the column height per degree of temperature change. So if you get a big change in height for a 1 degree temperature change, that's a very sensitive thermometer. If you get a small change in height for a 1 degree temperature change, that's a less sensitive thermometer. Linearity means that for every degree change, you get the same column height change. So if we're changing from 1 to 2 degrees, that produces the same height change as going from like 88 to 89 degrees, for example. So that's what we mean by linearity. So a mercury in-glass thermometer is placed in an insulated beaker of water at 60 degrees. The water is heated at a constant rate, and what that means is we're supplying thermal energy the same amount every second. The temperature of the water is measured and recorded on a graph. Okay, so this is our graph. So state the effect of the heat supplied during a period of 0 to 5 minutes. Okay, so supplying the thermal energy up to 5 minutes causes the temperature of the water to rise. And during the period of 10 to 15 minutes, it's causing the water to boil or to change state from liquid to gas, because you can see the temperature isn't changing anymore, but we're supplying energy, so that must be a state change. So the diagram shows the path of a few air molecules and a single dust particle. The actual air molecules are too small to show on the diagram, and that's exactly what we'd expect from like a Brownian motion experiment. We can see the dust or the smoke or whatever we're using, but we can't see the air particles, but we can see the effect of those air particles. Explain why the dust particle undergoes small random movements. So the key is the air molecules collide with the dust particle, and so the air particle molecule changes momentum, and that exerts a force. And then the air molecules are moving randomly because they're a gas and they're traveling at high speed. And so they're going to collide from all sides. And that's why they're going to get these small random changes in motion, because we've got collisions coming from all directions due to the random motion of air molecules. So the diagram shows the path of a few molecules leaving the surface of a liquid. The liquid is below its boiling point. So the fact that they're leaving the surface tells us, so it's not boiling, so this must be evaporation that we're looking at. State which liquid molecules are most likely to leave the surface. So it's not asking you to find which of the arrows it is, it's asking you to realize this is evaporation, so it's the highest energy molecules that leave the surface. So explain your answer. Well, the intermolecular forces are strong, which means a large amount of energy is required to escape, which is why only the highest energy molecules can escape. So the diagram shows a shallow dish containing a liquid that evaporates easily. The bulb of a thermometer is held in the liquid. A jet of air is blown over the surface of the liquid so that the liquid evaporates quickly. Because remember, a fast-moving air over the top of the liquid increases the rate of evaporation. So state what happens to the reading shown on the thermometer. Well, evaporation causes the liquid temperature to drop, so it's going to decrease. Explain your answer in terms of the behavior of the molecules. Well, if the high energy molecules escape, that's going to decrease the average kinetic energy of the remaining molecules, which means the temperature is lower. Because remember, temperature is a measure of the average kinetic energy of the molecules. Okay, so that's what's going on. Let's start one example in everyday life where this effect is demonstrated by this experiment. So sweating is a classic example of this. The reason that we sweat is it decreases the temperature of the liquid, and that decreases our skin temperature therefore as well. So on a hot day, a child drinks all the water in a plastic bottle, then screws the cap back on tightly so the bottle contains only air. Okay, so we've got a fixed mass of air inside our bottle. She throws the bottle into a waste paper basket where the sun shines on it. After a while, in the sun's rays, the air in the bottle is much hotter than before. State what has happened to the pressure of the air in the bottle. Well, if the temperature rises, the molecules are moving faster, they're going to have more collisions per second with the container wall, and they're going to have a harder collision every time anyway, so that's going to give you a higher pressure. So that's really what I'm talking about. So higher kinetic energy of molecules, so they're moving faster. So you have more collisions per second, and each collision has a bigger momentum change, and that's going to give you a bigger force. Okay, so also in the wastebasket is a broken glass bottle containing a small quantity of water, as shown. As the sun shines on it, the volume of water slowly decreases. State the name of the process causing this decrease. That's evaporation, because it's not going to be at 100 degrees, so it's not boiling, so it's got to be evaporation. In terms of the effect of the sun's rays on the water molecules, explain your answer to this one. So absorbing energy from the sun means there are more high energy molecules which have sufficient energy to break out of the strong intermolecular forces and therefore escape as a gas. So when a certain amount of heat is supplied to 1 kilogram of insulated aluminium, the temperature of the aluminium rises by 1 degree. In what form does the aluminium store the energy that has been supplied? So the technical term we should be using is internal energy. So when something's temperature rises, we say its internal energy is rising, but we could also describe that as thermal energy or the kinetic energy of the atoms. But you have to be specific. If you want to talk about kinetic energy, you have to say of the atoms or of the molecules there. But we call it internal energy. The same amount of heat is supplied to 1 kilogram of insulated copper. The temperature rise of the 1 kilogram copper block is greater than the temperature rise of the aluminium, so more than 1 degree, essentially. Explain in terms of thermal capacity why this is so. So aluminium has a larger specific heat capacity, so it takes more energy to give you a 1 degree temperature rise than copper, which clearly requires less because it's changed by more than 1 degree. So an immersion heater is put into some crushed ice at 0 degrees. The immersion heater is switched on, okay? And we've got an insulating beaker surrounding it. So on the diagram, sketch the graph of the temperature against time up until the time when all the ice has melted. So it's going to stay at 0 degrees up until the ice melts, because temperature does not change during a state change. Incidentally, after it's all melted, then we'll see this kind of shape where the temperature starts to rise, but not until all the ice is melted. The heat is left switched on after all the ice is melted and the temperature rises. After some time, the temperature stops rising, even though the heater is still on. Suggest why it stops rising. Well, we must have reached its boiling point, or 100 degrees, so we're going through another state change, because if temperature stops changing, that means a state change is occurring. State what happened to the energy received by the water whilst this is happening. So the molecules use the energy to overcome the intermolecular forces and escape. So that's why temperature isn't rising anymore. So they're using the energy to escape instead of using it to increase the average kinetic energy, essentially. So the diagram shows the apparatus that could be used to measure specific latent heat of ice. So we've just got a heater, some ice that's melting, and we've got a beaker to collect the water that's changed state. Okay, so describe how you would use the apparatus. You may assume that ice at 0 degrees and a stopwatch are available. State all the readings you'd be needed at each stage. So what we're going to do is we need to first figure out the power that we're supplying. So I'd use a voltmeter and ammeter, and power is equal to current times potential difference. So you turn on the supply and measure 10 minutes using a stopwatch. And then at the end of the 10 minutes, I'm going to measure the mass of liquid water, because that's the mass that's changed state. And using the power, the time, and the mass, we can figure out the specific latent heat of fusion of ice. So an experiment, 120 grams of ice at 0 degrees is to be melted. The specific latent heat of ice is 340 joules per gram. Assume all the energy from the heater is used to melt the ice. Calculate the expected time with a 60-watt heater. So the thermal energy to change the state of all of that, we can use Q equals ml, and that gives us a value of 40,800 joules. We also know that power is energy divided by time. So the time taken is going to be energy divided by power. So we know it's 60 watts, so we divide 40,800 by 60 gives us 680 seconds. Okay. When the experiment is carried out, the ice melts in slightly less time than the expected time. State one reason why this happens. Well, ice is below room temperature, so energy is going to be transferred from the surroundings to the ice. So actually the heater doesn't have to supply as much energy as it would have if we didn't have heat exchange. So that's why. So there's one modification to the experiment that will reduce the difference between the experimental time and the expected time. Well, fit insulation around the ice to prevent that heat exchange with surroundings or as much as possible. So here is a list of solid materials. Put a tick in a box alongside the materials which are good conductors of heat. So essentially, this is a question of identify the metals. So these are the three metals. Those are the three good conductors because they have free electrons. That's what makes them a good conductor. State the word we use to describe materials that are poor conductors of heat. Well, they're called an insulator. From the list of materials, state which would be suitable for use as the base of a cooking pot. Well, we need a cooking pot to transfer thermal energy from whatever the heat source is to the food as quickly as possible. So we need a good conductor. Whereas the handle, we want to not get hot because somebody's going to hold it. So we need it to be made out of one of the insulators. Water is a poor conductor of heat. A beaker of water is heated as shown. All the water heats up quite quickly. State the process by which heat spreads most rapidly through the water. That's going to be convection. In liquids, convection is the dominant energy transfer method. State why the heating element is placed near the bottom of an electric kettle. Well, we want to create a convection current. And a convection current is formed by less dense hot water rising and cooler, more dense water falling. So we need to heat from the bottom, so then water from the bottom rises up, and then water at the top can fall down. If we heated from the top, all we do is just keep hot water at the top because we're just forming hot, less dense water at the top and we're not setting up a convection current. Logs of wood are burned in a campfire on the ground. A person is sitting nearby. State two types of energy that the burning logs possess. Well, they are a fuel, so they're going to have chemical potential energy, but they're also now hot, so they're going to have internal energy. State the main method of heat transfer by which energy from the fire reaches the person sitting nearby. The main mechanism is radiation, or infrared radiation to give it its full name. A spark jumps out of the fire. State the name of the type of energy the spark possesses due to its movement, kinetic energy. The spark lands on a person's hand. State which method of heat transfer causes the person to feel the spark. That's conduction. When things are in contact with each other, conduction is the main energy transfer method. Pain is caused by the spark, makes the person stand up. State the type of energy that's increased. Well, the person's center of mass has moved upwards, so that's going to increase their gravitational potential energy. State the type of energy stored in his body that enabled him to stand. Well, chemical potential energy. That's what our muscles transfer into all the different forms that we might produce.